Welcome back, Math 1910. We are Chapter 5, Section 2. Last section, we learned how to take the derivative of natural log functions. This section, we're going to learn how to take the antiderivative, or do differentiation, right? We're going to integrate using natural log functions. Okay, so very important for us to be able to do this, and it will also work with trig functions for us as well. So let's get right to it. Just reviewing the differentiation rules, right? The derivative with respect to x of the natural log of x is 1 over x, or, right, we also had u substitution if we had, some other larger type argument for the natural log of x. We did u substitution. So the derivative with respect to x of natural log of absolute value of u was du over u. Now, if we look at theorem 5.5, that's the log rule for integration. So if we have the integral from 1 over x dx, that equals natural log of the absolute value of x plus c. Please, it's very important that you understand you must write the absolute value of x every time you take the or integrate or take the antiderivative of 1 over x using the natural log function. And then also, like before, if we had some sort of polynomial or larger function that's 1 over that function, all right, we would use u substitution. So the integral of 1 over u du is equal to the natural log, the absolute value of u plus c, right? And then we would substitute in what we designated for u in after that. Okay, so if we do this, all right, an alternate form for us is to be able to use u prime or du, all right, more common du if you do this. But you can say that we have u prime over u times dx, as long as you define as du, right, has to be u prime dx. So, before we've solved for dx in terms of du for substitution, it really doesn't matter which way you do it. You can do it either or. So let's take a look at this example here. First integral, we want to integrate 2 over x dx. So first step, let's pull that 2 out. It's a constant, all right? So pull that in front of the integrand. So we're going to have 2 times the integral of 1 over x dx. You're right. Now, before we could rewrite that as x to the minus 1 and work through it and do that sort of thing. But now we're going to do it using logs. So we automatically already know we have the integral of 1 over x dx. So we're able to use natural logs now to do that integral. And remember, the integral of 1 over x is the natural log of the absolute value of x. So our final answer here would be 2 natural log absolute value of x plus c. Now, we do have a power in front, right? We could rewrite that using properties of logs as well when we do that. So we could rewrite this as natural log of x squared plus c. Now, we can do that in this case, all right? The absolute value doesn't matter in this case because with the 2 being an even power, if we square it, or if it was to the 4th or to the 6th, we're going to end up with a positive answer. So just to reiterate, we got an even power. The absolute value piece doesn't necessarily need to be used, okay? Because no matter what we do, that answer will be, or will never be, negative in that case. All right, let's do something a little harder. All right, we want to find this indefinite integral of x squared plus x plus 1 divided by x squared plus 1. Not necessarily an easy u, all right, because we have polynomial in the numerator and the denominator. So what we might need to do first, all right, is reiterate an old school or redo an old school kind of technique, is doing long division first to simplify the polynomial. All right, so we're going to do that. We're going to take x squared plus x plus 1 and divide it by x squared plus 1. All right, so when we do that, all right, and we do our division, we end up with, just 1 plus x is our remainder. So we write our remainder over what we divided by. So that's where we get the x divided by x squared plus 1. And that's our remainder over what we divided by doing the long division. So we end up with being able to integrate 1 plus x over x squared plus 1. That helped us eliminate one of those x squareds in the numerator so that we can separate this out and have a better choice to use natural log for our integration. So we can rewrite that integral as the integral of 1 plus x over x squared plus 1 dx. Then we can separate that integral into two different integrals. The integral of 1 dx plus 1/2 times the integral of 2x divided by x squared plus 1. Alright, so we went from what down here at the bottom, okay, x over x squared plus 1, okay, and then we rewrote it as two separate integrals. Now the reason that we have the 1/2 in front and now there's a 2x in the denominator, that's going to help play kind of a key role when we do our du. So we really multiplied by 1 in the form of 2 over 2. Alright, so that's going to help us work through that issue here. So that's where the 1/2 and the 2 come from. We're just multiplying by 1 in the form of 2 over 2. And we knew that because our denominator has an x squared plus 1. Okay, so if that's our u, we know that our du is going to have a 2x in it. So our methodology, we kind of have to be thinking ahead there as we do this. So when we do this integral now, alright, the integral of 1 dx is just x, plus we have 1/2 times the natural log of x squared plus 1. We used, alright, u was equal to x squared plus 1. Our du was equal to 2x dx. So we had du over u when we did that integration. So that's why we have the natural log of x squared plus 1. Okay. Now, you can take the derivative of that function and see if you get, you can bring that 1/2 up if you want to, so it could be x plus natural log of x squared plus 1 to the 1/2 plus c, and then that 1/2 does what? It gives us a square root sign. So we could have this as x plus natural log of the square root of x squared plus 1 plus c. Okay. I'm not going to read through these guidelines. These are something that you might want to write down in your notes as you go through it. Obviously, number 4, you guys aren't probably subscribing to Wolfram Alpha or anything like that. Or if you have the CAS system, I guess, on your calculator, it'll do those sort of things for you. But go ahead and write down these guidelines, and kind of go through. Step 3 is kind of more the important one. All right, 2, you should be able to see most likely if you got a good U or not. But identify, if we have to use long division or break the integral up into multiple integrals or things like that. All right, so let's do this. We have a differential now. We have dy over dx equals 1 over x natural log of x. Okay, so for us, when we start writing that integral, we need to put everything in terms of y. Now we've integrated both sides, so there's a step kind of missing here. When you integrate both sides, right, we move dx to the other side and we integrate y. Okay, to do that. When we integrate dy, we just get y. So that's where the y comes from on the left-hand side. We did integrate the left-hand side already. The right-hand side remains as the integral of 1 over x times the natural log of x dx. Okay? Now, since we have a quotient in the denominator, first, let's take a look at the log rule. Usually, that's where we want to go when we have some sort of division, all right, and everything's in the bottom. So you could choose a couple different ways for u. We could make ux, we could make u natural log of x, but our goal when we're trying to do that is to make sure that we fit the form of du over u, all right, when we do that. So that doesn't necessarily always, work out in our case, but we can see that if we have this other choice here where we let u equal the actual natural log of x, okay, it's going to work with our du is equal to 1 over x, okay? So we can rewrite our integral. We're going to divide the numerator and the denominator of our integral by x. So that way that it fits our u du. Alright, so as long as we let u equal the natural log of x, alright, and we divide by 1 in the form of x over x, so our numerator of our integral becomes 1 over x divided by natural log of x. Alright, that cancels the x that's in the denominator and creates a 1 over x in our numerator. Well, that's important because if u is natural log of x, our du becomes 1 over x dx. So we're able to replace the numerator with du, alright, over u for the denominator, so we can do our normal integration. Okay? So that gives us, you're going to see a lot of these written as u prime. I'm going to call it du. U prime, du, they mean the same thing. So now we're in the form that we're used to. We've got u prime over u dx. All right. When we do that, applying the log rule tells us that we get the natural log of the absolute value of u plus c. Now we have to replace our choice for u back in. So in this case, it's kind of weird, right? We have the natural log of the absolute value of the we have the natural log of the absolute value of the natural log of x plus c when we do this substitution back in. Okay? So, make sure that you put it back in. Don't forget your plus c because we're doing indefinite integrals. So our final answer here is y equals the natural log of the absolute value of the natural log of x plus c. All right, let's do one more example here, doing trig functions. Okay? We want to integrate tangent of x. All right, so there's not something nicely that we can take the derivative of, that's going to give us, tangent or things like that. So we want to integrate tangent of x dx. So our first step, we want to rewrite tangent. All right, so that it can get us some formulas that we can play with and work with. So if we rewrite tangent as sine over cosine, we get the integral of sine of x divided by cosine of x dx. Okay, so next, we have to kind of choose what our u is going to be. So for us, in order to use the log rule, we're going to choose u to be what's more complicated, which is the denominator. All right, so if we're going to let u equal cosine of x, du, all right, is going to equal minus the sine of x. So we have to rewrite our integral there, or we'll have the negative that we can kind of bring out in front. So we want to make sure that we use the opposite of negative sine of x. We're doing that, we're multiplying 1 by 1 in the form of negative 1 over negative 1. All right, we're doing that because when we take the derivative of cosine, we get minus the sine, and we need our du dx to cancel out when we do our integration. All right, so we are in the form here, opposite the integral of du over u dx. All right, we did our u substitution. When we do our log rule here, we get the natural log of the absolute value of u plus c. And now we substitute in back our u, which is cosine of x. So we end up getting negative natural log absolute value of cosine of x plus c. All right, so write these down. Okay, these are on like the inside covers of your book handout that I've given to all you guys, or if you're strictly online, that's on my website as well. So you can look at the integrals of the 6 basic trig functions. Okay, some we've already done, right? We've already done sine, cosine, secant, cosecant, things like that before the other way. But now, or secant squared and things like that. But now we can do the other trig functions: tangent, cotangent, secant, and cosecant. We did cosecant squared and secant squared before. So now we can do that. And notice these these four, right? Tangent, cotangent, secant, and cosecant all involve being able to do the integration using the natural log function. Okay, so very important that we understand how to do the natural log and apply the natural log to integrals and things like that. Makes it simpler when we have some sort of quotient rule, where we have some sort of trig function or polynomial or some sort of maybe complex function that is in the denominator. All right, guys, I'm going to do some more examples live in class and things like that. But as usual, if you have any questions, email me. Let me know if we need a team meet or Zoom meet or anything else like that. Else, guys, have a great day. See you in class.